current would change if you change voltage, that ratio. Now, this is also a hill climbing algorithm. So if we have, this is P, this is V. If you're here, P is equal to V times I, right? So if I find dP over dV, if I take derivative of power with respect to voltage, I would get d derivative of V times I divided by dV. Okay, can you take this derivative? You should be able based on your calculus knowledge, right? So if I do this, it's going to be equal to dV times I plus V times di over dV. So this is going to be equal to 1, right? So it's going to be I plus V times di over dV. So basically dP over dV is going to be I plus V times di over dV. Or if our steps of voltage changes are small enough, we can write this as delta P over delta V is equal to I plus V times delta I over delta V. Okay, so why is this called incremental conductance? What is this? This is conductance, but it's a change of the conductance. So this term is incremental conductance. Okay, so if this is the maximum power point, what is dP over dV at the peak? It's equal to 0, right? Right, so if we make this one equal to 0, it basically means that dP over dV is equal to 0. Means that we are at the peak. At this point, dP over dV, it's gonna be positive or negative. As you increase the voltage, power goes down, so this is gonna be negative. At this point, it's gonna be positive. Okay, so here what happens is that we measure the conductance, instantaneous conductance, and the incremental conductance. Okay, and based on that we can find the incremental power changes. If that's positive, we know that we are on the left side. If it's negative, we are on the right side. Okay, and by changing voltage accordingly and measuring both incremental and instantaneous conductance, we can eventually move to the hill. So we're climbing the hill here. Okay, so this is the most accurate method. We can end up at the hill using this method, but it is very complicated because you have to measure many things. Okay, you have to measure many things, and in order to be accurate, your step means like the changes that you have to apply, in this case delta V, has to be small enough so that the computation time it's going to be big enough. Most of the time the computation time in Mppt algorithms is not that, like the time constant is not that important, because usually the sun or the irradiance of the sun doesn't change that fast, right? Like it doesn't change like based on seconds, or like based on like, you can see that like it changes like every minute or so, and usually our time constants are in the order of milliseconds or microseconds. So that shouldn't be a problem, but it basically adds to the computation time, and also like it means that you have to measure so many things. So these are the common methods that we have for MPPT algorithms. So we saw that there are mainly 4 methods: fixed voltage, which is not very common; fractional open circuit voltage; perturbation and observation; and incremental conductance. Okay, so when you want to compare different algorithms, there are many things that you have to consider. Okay, so one of the things that you have to consider is like how easy this is to implement in terms of software, like the programming, in terms of hardware, what do you need, and how accurate this is, accuracy. Okay, so let's just like do a very quick comparison between or among these methods. So for this one, as you remember, fractional open circuit voltage, we just like measure the open circuit voltage, right? And then the voltage of our operating point voltage is going to be a fraction of that. So we basically need a voltage divider. So it can be a resistive voltage divider. So in terms of hardware, this is very easy to implement. In terms of software, it's also very easy. You just like need to calculate just so you just basically you have to multiply the open circuit voltage by a factor. So it's very easy. You don't have to do many calculation. In terms of accuracy, it's not very accurate, right? It's maybe good for a simple solar cell, but for a panel or an array, because of the partial shading, it's not very effective. It can be a good estimate, but it's not really very effective. Now let's talk about this one, incremental conductance. So you saw that in terms of software and hardware, this is very complicated. You have to have like measurement for the for the voltage, current, incremental voltage and current. You have to do lots of multiplication. You need to remember the previous values. So in terms of memory, it's also like not very efficient, but it's very accurate. It's very accurate. Okay. So this is probably the second most common after PNO. The PNO is somewhere between, right? So it's kind of like, what is the term? Like the sweet spot. Like this is basically a compromise between